Okay, so this video is going to primarily cover the integration that we looked at this semester. However, before I transition over to that, I want to go over this implicit differentiation, which I didn't cover on the last packet. Remember, with implicit differentiation, what you think about is you're just going to go through and differentiate everything, applying all your derivative rules. But whenever it comes to y, you got to remember the chain rule, and you're going to differentiate and then multiply it by the derivative of y, dy dx. We'll just call it y prime. So look, here I've got 2x. So if you look at this one, I've got 2x plus, now let's do the product rule. Derivative of the first times the second plus the derivative of the second times the first. Well, here's the derivative of the second. Taking that derivative of y, I got to tack on a y prime equals 0. The derivative of 4 is 0. So this is the main difference. Whenever we differentiate with respect to y, we have to remember y is equal to some function in terms of x. Okay, it's some function of x. So we got to remember to multiply by the derivative of inside, the dy dx. So now I get my y primes together on one side. So here's what I've got. I've got 3x squared y prime equals negative 2x minus 2xy cubed. Just bring all that to the other side. And then I divide. I just solve for y prime. Negative 2x minus 2xy cubed over 3x squared y squared. There. That's it. There you have it. You have the derivative, dy dx. That's what y prime is in terms of x and y. Now what I want to do is look at this one, b. So we've got 3x squared plus 3y squared. Don't forget the y prime. Plus 4 equals, now there's just a y there, so that's going to be y prime. I gather all my y primes together, move everything else to the other side. So here's what I've got. I've got 3x squared plus 4 equals y prime minus 3y squared y prime. Factor out the y prime. See? I get that. And then just divide by the coefficient of y prime. So I got y prime is equal to 3x squared plus 4 over 1 minus 3y squared. There, that's it. That's the process for all of these. So in this next one here, look what we've got. We've got cosine x plus cosine y. Don't forget the y prime equals 2x. Okay. Now I just need to solve for y prime, which is going to be easy. We've got y prime cosine y equals 2x minus cosine x. Just divide by cosine y. And there you have it. There's your derivative dy dx. Now, really, these are all pretty straightforward. You have to be careful when you have products like this, x to the fourth, y to the seventh. You have to remember you're still applying the product rule. So this is 4x cubed y to the seventh. That's the derivative of the first times the second, plus the derivative of the second times the first, plus the derivative of y. Yeah, like that. Okay, so you just have to be sure and apply the product rule. Now, solving for y prime, I get y prime is equal to 1 minus 4x cubed y to the seventh divided by 7 x to the fourth, y to the sixth plus 1. See, don't forget, when you're factoring the y prime out of this, there's a 1 here. So don't forget, that's a mistake sometimes people make. Okay, now we get into integration, and what we noticed about integrals was that they are sums. They sum up an infinite number of things. That's what they are. They're summing machines. So let's see how we would apply that here. We've got the integral of from 0 to 1 of x squared dx. So we realize, okay, an integral is a limit. Okay? And it starts off this way. Okay? Now, what we want to do now is we want to say, okay, if I divide this interval from 0 to 1 into n equal parts, what would it be? Well, it would be the width of the interval over the number of parts. That's like our delta x. And then we have 1 over nk squared, like that. So this is just, where this came from, we can go back and talk about that, but this is just meant to be a review, a real quick reminder. Okay, we replace x with delta x times k, and then we have delta x. So look, on this one over here, we have the limit as n goes to infinity. K goes from 1 to n. Now, delta x, the width of the interval, 2 minus 1 over n. Okay. Now, I'm going to replace x with 1 plus 1 over n k squared. Now notice, remember that this and this add up to this, right here. And this right here, this is the bottom limit. Okay, it's this one. Okay. Now let's look at this one. We've got the limit as n goes to infinity. K goes from 1 to n. Now let's see, 6 minus 4, that's 2. Okay. Now, here's what we're going to do. We're going to do 4 plus 2 over nk squared. See, the 4 came from right there. And 4 and 2, that's 6. 4 and 2 is 6. Plus 2 times that whole thing, that same thing. Yeah, like that. Okay. So we need to be able to recognize, okay, this integral, it's a limit of a sum. It's a limit of a Riemann sum. Okay. Now we go backwards. We say, okay, now this is going to be an integral. Notice there's nothing in here. This is just 6 over nk. So this is going to go from 0 to 6. See? 6 right there. And this is x cubed. See, this is my delta x xk. That's raised to the third power. Over here, I've got the integral from 1 to 3. See? 1 and 2 adds up to 3. And this is going to be x cubed. See? Just replace that in with x. Okay? This integral down here, it goes from 2 to 6. See? From 2, and then I add 2 and 4 and get 6. X squared plus 5x plus 2. Okay? The delta x. And here's the x squared, the 5x, and the plus 2. And there you have it. So this is us just recognizing what an integral is, just when we're trying to define what a definite integral is. Now, we also are indefinite. Yeah, no, a definite interval. Now, as far as applying, in a, as far as actually evaluating these intervals, these definite intervals, we use the fundamental theorem of calculus. And it says get the antiderivative and then plug in 1/3 times 1 minus 1/3 times 0 cubed. And there it is. And of course, this would just be 1/3. Okay, we do this on all of them. The antiderivative of cosine is negative sine. Yeah. No, not negative sine. I'm sorry. Sine. Sorry about that. I hope you caught that. So it's just sine, okay? Because the derivative of sine is cosine. So now we plug this in and we get sine of pi over 4 minus sine of 0, which is square root of 2 over 2 minus 0. So, okay. Now this one, we've got 1 to 4 x to the 1/2. We get the antiderivative, just using the power rule for integration. And this is going to be 1 over 3/2 x to the 3/2 from 1 to 4, which that's going to be 2/3 x to the 3/2 from 1 to 4. And that's going to be 2/3. And let me just factor that out and go 4 to the 3/2 minus 1 to the 3/2. Okay, let's see what that is. 4 to the 3/2. Well, the square root of 4 is 2, and then 2 cubed is 8 minus 1. So it looks like this is going to be 14/3. Okay. Now, so those were when we were talking about definite integrals, that's when, we get the antiderivative, then we plug in the top limit minus plugging in the bottom limit. But now, if we don't have those bounds of integration, the limits of integration, then we're just finding the antiderivative. And sometimes that can be challenging. So we need some techniques. And one technique that we looked at was substitution. So I'm going to use substitution here. Notice I can let u equal x squared plus 7. Then du is equal to 2x dx. There's 2x dx. So I can immediately rewrite this as just u to the 5th because I replaced 2x dx with just du. And of course, x squared plus 7 I replace with u. So this is going to be 1/6 u to the 6th. And when we're dealing with indefinite intervals, we put the plus c, the constant, because there are infinite number of antiderivatives and they all differ by a constant. Okay, now for this next one, I'm going to let u equal x squared plus 4. Now remember, what we're thinking of is when we do the du, we want to somehow be able to cover the rest of the integral, the integrand there. So look, du is equal to 2x dx. That's almost what I've got up there. I've got 2x dx up here. I've just got an x. So let me divide out the 2. And what you have now is you have 1/2 u to the second du, which would work out to be 1/6 u to the third, because we're doing we're going to get in the bottom, we're going, well, let me show you. We've got 1/2 times 1 over 2 plus 1, u to the 2 plus 1. So there's where I got the 6 in the bottom. 1/2 times 1/3. Okay. Now on this one, once again, we're going to let u equal x cubed. Then du is equal to 3x squared dx. Ah, I don't want 3x squared dx. I want x squared dx. So let me divide by 3. And now let's see what I've got here. I've got 1/3 sine u. Yeah, yeah, that's it. So this is going to be 1/3 cosine u du, and it's minus. The antiderivative of sine is negative cosine. Oh, look at me. I put a du there. What? What kind of craziness? Plus c. I meant to put a plus c. Okay. Now, for this one down here, I notice that x squared plus 1, the derivative of that is just 2x dx, which is that. So what we've got is du over u, which is log u plus c. Ooh, log absolute value. Now, that's a good habit to get into. Of course, in this case, we've got x squared plus 1. That can never be negative. So we could get away with just calling it log u in this case. But normally it's log absolute value. Okay. Over here on this one, we got, let's see here. This looks like a tricky one. Let u equal log x, then du is 1 over x dx. Ah, that's kind of tricky. There's 1 over x dx. So this just turns out to be u du, which is 1/2 u squared plus c. Okay, now we got this tangent. Well, somebody might say, well, how are you supposed to use substitution on that? Well, if you recognize tangent as sine over cosine, now notice I can say, well, let u equal cosine. Then du is negative sine, which is what's on top, except we've got a negative. So negative du is equal to sine x dx. Ah, so here we go. We got negative du over u. That's negative log absolute value of u plus c. Okay, let's see what's next here. Now, we want to find the bounded area. So we're looking at one of the applications of integrals, bounded area. So let's take a look at this first one here. We've got a couple of functions. We've got, here is x squared, and then we've got 8 minus x squared. And it looks like what I want is I want all of this area right in here. Now, I need to find what this point is and what this point is. I need to find the intersections so I'll know how to integrate. I need to know my bounds of integration. So I take these and set them equal. And I get 2x squared equals 8, or x squared equals 4. That means that x equals plus or minus 2. So it looks like this is negative 2 over here, and this right here is positive 2. But I couldn't help but notice some symmetry there. So I think what I'm going to do is I'm going to integrate from 0 to 2 and just double it. I take the top function minus the bottom function. See? I get all that area, and then I subtract off what I don't want. Okay, so this is going to be 2, the integral from 0 to 2, 8 minus 2x squared. About out of room here, but I've got 2, and here's 8x minus 2/3 x cubed from 0 to 2. Hey, let me reclaim some of this room up here. So I've got 2 times 8 times 2 minus 2/3 2 cubed. Yeah, that's it. That's it. I guess we can go further. Here's 16 minus 16/3. And I guess 3 times 16 is 48. So I've got 2 times 48 minus 16/3. And I think about it that it's going to be what 64/3 maybe, because this in here, 48 minus 16 is 32. 32/3. Yeah, I think so. I think that's it. We got that. Okay, now this next one I threw in one that is opening left and right instead of up and down. So we've got, let me look up here. We've got this function. Here's y squared, x equals y squared. And then we've got this one, which is 18 minus y squared. So we're going to be integrating with respect to y. So I set these equal. 18 minus y squared equals y squared. And I get y equals plus or minus 3. Now I need to set up my integral. So here's what I'm going to do. I'm going to integrate. I take the rightmost function minus the left. And it looks like there's some symmetry here, so I'm just going to go 2 times 0 to 3. I'll just get this top and then double it. To be on the safe side, you can integrate from -3 to 3, if you don't recognize the symmetry there, but this one is symmetric. So we've got 2, 0 to 3, 18 minus 2x squared. So let's see what that's going to be. Here we go. 2, 18y. Ooh, look at me. Look what I did. That's not good. We're integrating with respect to y. Not there. Not there. I'm losing control here. So this is y and this is y. Yeah, sorry about that. So here we go. 18y minus 2/3 y cubed from 0 to 3. I'm integrating with respect to y. You can see how that's going to be easier than trying to integrate with respect to x, because x is a function of y is not a function of x. Okay, now let's see what we got here. We got 2 times 18 times 3 minus 2/3 3 cubed. There we go. And then you can just do the arithmetic. Let me just move on from that. I don't want to stretch out the video too long, even though I do so love making the video, but got to keep it short. Okay, now we got this one. Okay, so uh, here we go. We've got the square, we've got the x squared, and then we've got x, okay, like this. Now this is going to intersect at 0 and 1. So we're going to go from 0 to 1, x minus x squared. And we would find the intersection just by setting them equal again. X squared equals x. And what I get is I get 1/2 x squared minus 1/3 x cubed from 0 to 1, which is going to be 1/2 minus 1/3. Okay. I guess that's going to be 1/6. Okay. Now, let's look at this one here. We've got x squared minus 8. Okay, so it's going to be down here, right? It's the x squared function that's been shifted down. And then we've got the negative x squared. So that one goes like this one, okay, goes like that. Now this one is going to intersect. So we've got x squared minus 8 equals negative x squared. So that's going to be x equals plus or minus 2. And once again, there's symmetry. There's symmetry involved in this. Okay. Now, so here's what I'm going to do. I'm going to go 0 to 2 and double this. I'll take the top function, okay, which is negative x squared, and I subtract the bottom function. Okay. So with these, we're always taking the top function minus the bottom function, even if they're both underneath the axis. Okay. Now, if I work through that, I've got 2, and here I've got negative. Well, let me just write it this way. I've got 8 minus 2x squared dx. That looks familiar. Oh, it does. It's right up here. We did this earlier. 8 minus 2x squared, 0 to 2. So it's the same problem, same outcome. Well, not the same problem, but you get the same integral. Okay, so that covers the second packet.